I want to continue with the stuff you guys were doing yesterday. So there's really two parts to this. First part is curve fitting, just mathematically. Once you click and close. Yesterday we did really all I did yesterday that you saw was went through an example where you were given the coordinates of the vertex and another point on a parabola, and you had to fit the parabola to vertex form. Okay. So that was yesterday's. I'll make sure that that video gets put up on PlanBook today. I'll stay after and get all PlanBook updated with the stuff from the last couple days and the stuff from today. So today I want to do one more example like that, and we're going to look at it 3 different ways we could solve it. And then we're going to launch into applications of all this stuff, where we're going to start to look at some actual ways that we could really start to actually use math to solve some interesting questions. You're starting to just barely get to a point where you can maybe do just a little something with math now that's not just totally cheesy. Once you get to calculus, it just explodes, and there's all kinds of stuff you can really do. You actually can really do stuff that matters when you get to calculus. Everything up until then, it's just getting you ready for calculus. What about something like that? So this time, instead of being given 2 points, and I'm told that one of those points is the vertex, that was very helpful. Now I'm just giving you 3 random points on a curve, on a parabola. And I want you to come up with the equation of the parabola. Okay, and we want the equation in standard form, let's say. Okay. Equation of the parabola. Oh, come on. Okay, we're going to be able to plug in the parameters A, B, and C in standard form. How am I going to do that? What could we do? This is a little tougher. The example yesterday, because we knew one of the points was the vertex, it gave us 2 of the 3 parameters of vertex form. A, H, and K are the parameters we have to plug in for vertex form. It gave us 2 of those in just 1 point. That was pretty nice. This time, no such luck. None of those parameters are immediately given to us by these points. Okay, but you have an idea though. What do you think, Josie? Okay, how about that? Great idea. So what if we do something like this? Like if I take the point 0, 5, that's an ordered pair where the input value is 0 and the output value is 5. So that's telling us when x is 0, y is 5, right? So let's plug 0 in for x and see what we get. Well, if I plug 0 in for x, I get a times 0 squared plus b times 0 plus c equals y, which is 5. And how about if I add something up here? This is standard form. It's really equal to y, or f of x, right? Okay, form of it. That's the equation for a parabola in standard form. Well, I can simplify that a little bit. A times 0 squared is what? 0. B times 0 is 0. So this really just becomes the equation C equals 5, right? Okay, well, what if I take the second one? X is 2, y is 11. I can just plug those into my standard form, can't I? So I get a times 2 squared. What's that? Okay, so 4a plus b times 2 is 2b plus c equals 11. Okay?
At this point, we don't plug in the top one, right? Like, because C says C equals 5. We don't plug in.
Not yet, but we will. We will. We're just going to write down the 3 equations first. And then what about this guy? When x is 3, y is 8. So a times 3 squared is 9a plus b times 3 is 3b plus c equals 8. Well, look at that. That looks familiar, I bet. That is just a 3 by 3 system, right? You guys solved those. And this is an easy one because the top equation tells you the value of c, right? So it's pretty easy. We already know 1/3 of our parameters. We already know what c is. Now I could plug that value in there and there, couldn't I? Right? And then this becomes, if I do that, I get 4a plus 2b plus 5 equals 11, and 9a plus 3b plus 5 equals 8. And I could subtract 5 from both sides of both of those equations, and then I get a 2 by 2 system that's pretty simple. 4a plus 2b equals 6, and 9a plus 3b equals 3, right? Okay. Well, that's no big deal. What am I going to do with that one?
So you multiply the whole thing on top by 3 and the whole thing on bottom by 2
By
to make the b's the same.
to make the okay, right. So the top one, we're going to use elimination, aren't we? We don't want to use substitution here because no variable, I mean, we call it a variable here. No unknown is easy to isolate here, right? If I try to isolate a or b, I'm going to get fractions, right? And I don't want to substitute with fractions. So we'll multiply the top one by 3. I like that. If I distribute a 3 all the way through, I'm going to get 12a plus 6b equals 18. What should I multiply the bottom one by? -2, because I want to get opposite coefficients. So when I add them, they'll cancel. So if I multiply by -2, I get -18a minus 6b equals -6. And if I add those up, look what happens. We eliminate the b's. That's good. So a, I get -6a equals 12. So what's a? -2. Now what do I do to solve for b? Plug it in. Sure, I'll just take that guy and plug it in to that a. Top one's a little bit easier, right? And then that's going to give me, if I plug into the top one, I'm going to get 4 times -2 is -8 plus 2b equals 6. Last two steps to solve for b. Add 8, divide by 2, and what do I get? 7. Yep. 14 over 2, which is 7. So I found them. A is -2, B is 7, C is 5. And so when I plug those values into standard form, what was A again? -2. And B was 7. Then look what we get. Right? Okay, no big deal. Now, if we had some technology at our disposal, and you won't even need technology in college when you take linear algebra and you learn how to manipulate matrices without technology, you wouldn't even need technology, but matrices would make this a lot easier, right? I could take those 3 equations that we wrote, and I could write those as an augmented matrix, a system, as long as I write them in a standard form where the variables are in the same, probably alphabetic order. So the first one, isn't that the same thing as 0a plus 0b plus 1c equals 5? Well, there it is, right? The coefficient should be 0, 0, 1, 5. Red equation, coefficients would be 4, 2, 1, 11. Purple equation, 9, 3, 1, 8. And then once I get it written as a 3 by 4 matrix like that, I just do RREF, put it in reduced row echelon form. And isn't this telling me 1a equals -2, 1b equals 7, 1c equals 5? Quick and easy, right? Okay. How could I do this quick little see how well you remember this stuff. Would you walk me through how I could do this with Desmos graphing? Okay, I really don't need the graphing part. How would I do that? If I know the coordinates of 3 points that are on my parabola, what could I do? Put them in a table. So I go plus table, and then just enter the ordered pairs, right? 0, 5, 2, 11, 3, 8. Okay, now what? Okay, but I got to do y1 equals. Good. You're right, though. y1 tilde ax1 squared. I'm going to write this. I'm going to write out standard form with x1's in for my x's and y1 in for my y, right? So instead of y equals ax squared plus bx plus c, I've got y1 tilde ax1 squared plus bx1 plus c. And there it is. It's telling me the values of A, B, and C. How about that? And how about if we change let's make those red and let's make that blue. And look what you see here. There's my 3 points, right? Notice those are just 3 points on that parabola. 3 points defines a parabola. What's r squared? I did regression, right? But it's 1, isn't it? Yeah, because if I use 3 points, if I do regression with 3 points, it's going to be a perfect fit because any 3 points defines a single parabola, okay? Any 3 non-collinear points, okay? All right, so I will leave that for your notes. And now let's tackle an application. Okay, what about something like that? Okay, so what do we got going here? I gave you a little picture. A farmer wants to fence off some land for pasture next to a river. He's not very environmentally conscientious about this, evidently. So, but that's not our issue today. We're just trying to figure out. You're his paid consultant to figure out how to fence off this pasture, the configuration to fence off the pasture. He has 636 feet of fencing available to create 2 identical pastures as shown above. What dimensions would result in pastures with a total area of 24,300 square feet, first of all? That's the first question that's asked. Let's do one thing. I'm going to change that variable. What do you think I'm going to change that variable to? Doesn't really matter. This is sort of nitpicky, but I'm going to change that to a y. How come? This is what I always choose to do because it's vertical. It's vertical on the page. Y is like a vertical variable, right? And then the other variable that we might add here is x, right? Because we need another dimension. So why don't we call that dimension x? And I'm going to let x be the width of each pasture, but they're the same, right? Okay, so first of all, they want us to calculate. They want to come up with a configuration where the total area the total area is 24,300 square feet. Okay, total area. So I'm going to need an area function. Okay, what's the area of my pasture equal to, of the total times? Well, okay, but I don't want that specific one. I'm just talking about a general area function for these pastures based on the values I choose for x and y. What would the area of all the pasture land combined be? No, that's not area. What is it? 2x times y, isn't it? Right? It's just going to be the length of the entire area that we're using times the width, right? Length times width gives me the area of that big rectangle. Yeah.
So there's 3 lines that are equal to y. Why would it not be 2x times 3y?
Well, why would I need to multiply by 3? 3y isn't.
You have to include all of it because
Well, I am, because that distance is x, right? So that distance is 2x. Now, if I want to calculate, all I'm trying to do is calculate the area of this. I'll make it a purple square or rectangle. I just want the area of that purple rectangle, right? The width is y, and the length is 2x.
never mind, I got it.
Okay? All right, so area equals x times, or 2x times y, correct? Okay, good. Area is 2x times y. Okay, well, what's the problem with that? If I want to try to do the second part, what dimensions would result in pastures with a total area of 24,300? Yee. If I try to, I mean, what is this other information telling me? Like when it asks for this first part, I'll underline it in purple. They want to know what dimensions would result in pastures with a total area of 24,300 square feet. What's the significance of that number? That's A, isn't it? So that's what I would be plugging in for A. Well, then I would get an equation that would still have 2 variables in it. Can I solve a single equation involving 2 variables? No, I can't, right? I can only solve one equation if it has 1 variable in it, no more, right? So right now, I'm going to need some other additional information that's going to allow me to write area as a function of only 1 variable. Now, this is the kind of thing we're going to spend a lot of time in a couple of years doing in calculus. We do lots of problems like this. We won't typically probably work with this first question. We'll be doing things like trying to maximize quantities when we do optimization in calculus. So we'll be doing the second part. What dimensions would maximize the area of the pasture? Now, when we when we do calculus next year, we're doing calculus of a single variable. So we can only ever accommodate next year doing calculus with one type of input variable, not multiple input variables. That's multivariable calculus, and that would be down the road. That's a college class that you take after my AP calculus class. So we've got to somehow eliminate a variable. Well, we need a secondary equation. What we need to be able to write this as a function of 1 variable, either now or 2 years in calculus. We're still faced with the same dilemma right now. We got to write this as a function of 1 variable. So what I want to do is I want to find a second equation. We call it a secondary equation that relates the 2 variables. If I could find an equation that relates x and y, then I could solve for one of those in terms of the other and substitute into the area equation. We use that trick all the time in math. Yes? We don't know that. It could be, but it might not be. It might be that y is really small and x is really big, right? We don't know. Like these pastures, imagine that this thing could morph. We know the total, you see what I'm saying? Like we can change the dimensions around a little bit where we choose to allocate the fence, whether it's to the y dimension or the x dimension of the pastures. But there's still something going on. I would say in calculus, we haven't used any additional information, but if I just read that bottom question, what dimensions would maximize the area of the pastures? And let's make that the blue question, I guess. With no additional information, I would just say, well, that's easy. I'm going to make mine infinity by infinity, and I win. But what limits me so I can't do that? What do you think? Okay. Yeah, okay. And so the secondary equation, now this is kind of high level stuff, but you guys can handle this. The secondary equation, a lot of times in calculus, we'll talk about that as being the equation of constraint, because it's what limits the problem, so it can't just be infinite in a trivial question. What makes it a real world question that's not just, you can't just say infinity and be done. To constrain means to limit. So the secondary equation has to come from some limit that's placed on the problem. Well, the limit here is the fencing, isn't it? You only have so much fencing to use. And so our secondary equation has to come from that 636 feet of fencing. Okay, what does that tell us in terms of X and Y? What does that 636 have to do with anything? What do you think? Okay, it's the perimeter, kind of a modified perimeter. It's the fence, right? The fence distribution. So where are we going to fence on this picture? What would have to equal 636? 2x plus 3y. Yeah, right? I've got to do both of those horizontal fence lines and all three of the vertical fence lines. So we get the secondary equation, 2x plus 3y equals 636. Okay, agreed? Okay, so now I could solve for either one of those variables and substitute. Let's just say arbitrarily, for some reason, I wanted my area function to be a function of x. Okay, so I want to eliminate the y. Which variable would I solve for or isolate in the green equation? Y. Whichever variable I'm going to eliminate, that's the one I'm going to solve for and use to substitute. You get that? So if I solve for y here, I'm going to get y equals, 636 minus 2x all divided by 3. I'm going to put a box around it because that's my substitution equation. That's what's going to go in there for y. And then what happens? Well, then I'm going to end up getting the area equation. It's going to be a little bit different now. The area equation, A is equal to 2x times whatever y is in terms of x. Okay, now how many different kinds of input variables do you see now? One, just x's, right? So now I can call this a of x, which is nice. I've only got one input variable. So if I distribute the 2x, let's put this into standard form, okay? So if I distribute the 2x, I'm going to get, would you agree? If I distribute to the x term, I'm going to get negative 4/3 x squared, right? When I distribute to the other term, I'm going to get, so what am I going to get there? It's going to be this part right here. When I distribute the 2 here, I'm going to get 2x times 636 all divided by 3. Well, 636 divided by 3 is just 212, right? Isn't it? 2 times 212 is 424. Wouldn't I just get that if I distributed? I mean, I skipped through a couple steps, but that's what I get, isn't it? Okay, so there it is. So there's my area function. It looks kind of nice. It looks like a quadratic function in standard form, doesn't it? Ax squared plus bx plus c, where a is negative 4/3 and b is 424, right? Okay, that's good. We're familiar with those. We've worked with those a lot. Okay, now back to that purple question. We want to know what dimensions would result in pastures with a total area of 24,300. What could I do? Plug it in for area. Yeah, exactly. Plug that in for area. So then that's going to give me, when I plug in the purple information, I'm going to get the equation negative 4/3 x squared plus 424x equals 24,300. Okay, now we can just shift into algebra mode, right? We got to solve that equation. What are you going to do to solve that equation? What do you think? We could. We could multiply the whole thing by -3. We can do that. Okay, the whole thing. Everybody see that? If I multiply, I like that. Let's do that. If I multiply the whole thing by -3, then that's going to cancel. The first one's going to, I'm going to cancel the 3's and make it positive, aren't I? Right? So I'm going to get, that's going to give me positive 4x squared. When I distribute here, I'm going to get negative 1272 x equals, and this is going to give me 73,200. If I distribute the -3, that should be negative though, right? Okay, now what?
Do you have b squared?
Well, so what's your strategy going to be to solve this? Can you divide by 4? It looks like you can divide by 4, but there's still something else we want to do too. We still haven't done one thing. 73,900. Oh, you're right. 72,900, isn't it? Yeah. Whoops, you're right. Thank you. Good thing you caught that. Whew. Okay, what else do I need to do here? There's still something wrong with this equation. It doesn't look like it's in the right form to me.
Oh, you need to add 72.
Oh, okay, good. I got to set it all equal to 0, don't I? I've got to put it in standard form. Okay, so I could push this term over to the other side, and now I get 4x squared minus 1272x plus 72,900 equals 0. Okay, there still was a suggestion, could we divide everything by 4? Yeah, we could, right? Absolutely. I could divide everything by 4, and that makes this quite a bit easier, right? It makes these coefficients smaller. It's going to give me x squared minus 324x plus, I'm dividing by 4. So that's going to give me 18, and then 900 divided by 4 is going to be what, 225?
Your 324 is 318.
Oh, whoops. I said 320. What's that? 318. Oh, that's 318. Okay, good thing. Man, Dean, I'm glad you're checking my work here. Oh, I'm dividing by, I know I divided by 3. What the heck was I doing there, that second part? Jeez, I can't do any, I'm struggling a little bit, aren't I? Plus, and then what was I doing over here? It looks like I was, was that one right? If I divided by 4, I got 18, 225. Okay, oh God, about time, huh? Okay, so I've got a quadratic equation in standard form. How are you going to solve that one? I mean, you could. Those are pretty big numbers. You could.
You don't want to plug it into the.
I think I would just plug it in the quadratic formula. When the numbers are that, That's all right. I mean, we can just plug. I mean, we have calculators for that stuff, right? You definitely could complete the square on this too, though. That would be totally fine. If we solve this with a quadratic formula, I'm going to get x equals what? Is going to equal positive 318, negative b, plus or minus square root. Okay, and instead of squaring a negative, just square the positive, right? So you don't risk the chance of inputting a negative number incorrectly. 318 squared minus 4 times 1 times 18,225, all divided by 2, right? Okay, now I have no idea. I'm not even going to try to do that one in my head. What's that? Yeah. Definitely am there. I've been outclassed by some much smaller numbers today already. I don't know, but those are wrong. Was that our equation? That wasn't our equation. Yeah.
I'm like, there's an extra 4 there, and I don't know why.
Here, I'm going to go to another page, so I have a little more room to work here.
That was the only one I knew how to do.
Okay, so let's try this out then. So we've got $318 plus or minus. I'll do plus first. You can't do plus and minus both when I'm evaluating. I'll have to just copy and paste. So plus square root of 318 squared. Why is that in parentheses? I don't know. 318 squared minus 4 times 18,225, all divided by. So I'm going to skip to the right, push shift and highlight everything. Make sure you don't just put the division bar under the radical. It goes under the whole thing. Does it do it even on Desmos? It does. Oh, good. Okay, that's good. All right. Good. That's good. So I get 243 is that answer, right? If I take the positive one, I get 243. Okay. What if I take the minus? What's x going to equal if I take the minus? If I take the minus, let's find out. I'll just go back there and flip that to a minus sign, and I get 75. Oh, I can't do that. Okay. Okay, so what is that? What the heck? We got 2 values for x. So what's that mean? Yeah. Yeah, there are. The farmer's got 2 choices here. You're going to be in as good graces because as your consultant, you're going to say, well, take your pick, buddy. You can either let x equal 243. So you're talking about the dimension of each pasture that is parallel to the river, right? The dimension of that fence line could either be 75 or 243. Well, what if we take the 243 option, let's just say? So if we go back to our picture, so if we let x equal 243, what's y going to equal? How would I know? Where could I go to find out? Is there some place that's really obvious? What do you know? The one that's boxed. We always put a box around substitution equations because you almost always go back to them, right? So if I plug the 243 in there, I'm going to get 636 minus 2 times 243. So somebody figured this out. What's 636 minus 486? Oh, that's easy, huh? That's going to give us 250. 250 divided by 3 is 250 thirds, right? So we get one set of possible dimensions. Did I do it? Might I mess it up again? 286, 636 minus 286, 350, not 250. So 350, there we go. So 350 divided by 3. Man, I got to quit doing mental math today. I give up. Uncle. So there's one set of dimensions that would work. Okay, what if we take the other one? What was the other one again? It was 75. Okay, so let's make, these will be the orange dimensions. If we let x equal 75, I'm going to get 636 minus 2 times 75 minus 150. So that's going to be 480? 480 divided by 3 is 480 divided by 3. We know that. So that's 160? Oh, okay. So what is that? 162. Okay. I really am. I'm really struggling. It's an off day. So does everybody agree? Look, he's got two different dimensions. He could have pastures that have very little fence line along the river, or he could have pastures that have a lot of fence line along the river. Actually, hang on. Yeah, and much more fence line. That seems a little bit odd. I guess that's right. 75 and
No, so yeah, on that I plugged the 636 minus 486,
mhm.
and I got 150 divided by 3.
Oh, which is 50?
Yeah.
Okay, right. So then the orange dimension. No, hold it.
Because you didn't do
Two identical pastures.
you didn't multiply it by 2. You multiply x by 2. You just subtracted it.
I did.
Well, that was still wouldn't even.
I would probably take a larger one.
I don't know where.
Oh, 150 divided by 3. Yeah, it should be 50. I agree. I agree. Yeah, there we go. Okay. Okay, makes sense?
Why is the X so small for 75 and the Y so big?
Okay, well, because look, you have choices. Like, what would those look like? They'd either be real squished along this way or real squished along that way. Does that make sense? Okay.
I'm taking this really technical, like actually try and think it out, like show it in my mind.
Oh, that's the way we did it was we got the solutions were either 75 or 243. So if x is 243, I just plug 243 into this box and solve for y.
No, I know. I'm just trying to visualize it, and I'm
Oh,
getting a little confused. Because it's pastures, and I need to fix my pasture.
Oh, okay. Well, there you go. Okay, now how much time we got? 3 minutes. Man.
We don't have enough time.
Okay. Yeah. I'm ready to call it a day. I need to call it a day.